we've got Florence Maas-Garie, something close to that, sorry. And she will be talking to us about crystals on tableau and jeu du taquin.
Yeah, thank you. So this is some work that I've done through my master's thesis under the supervision of Franco Saliola. And I want to share how great I think results these are. Without further ado, I'll start my presentation. And so starting with why do we want to study tableaus in particular? Well, it's all about Schur functions, usually. It's always their fault. Why? Because, well, they're symmetric polynomials that are indexed by partitions, and they're actually a basis of the symmetric polynomials ring. So we're really interested in understanding them. And why we like tableaus? Well, they can be described combinatorially by a sum over tableau, which we'll see a bit more later. And I'll be interested in this talk in understanding products on tableaus. Why? Well, because we want to understand the product of the Schur functions, because they appear in multiple fields in mathematics, especially in representation theory and geometry. And in these fields, their product has a meaning. For example, in representation theory, the Schur functions, they're characters of the symmetric group. And their product helps us understand better the representations of the symmetric group, especially the square of a symmetric functions, but any product is fun. And why we'll use crystals? Well, crystal theory is kind of a newish field that establishes structure on combinatorial objects. So instead of kind of seeing them floating in space, non-related one to another, we're going to establish kind of connections between different objects. And especially there's a product defined on crystals, and we'll want our product on tableaus to be agreeing with this special product on crystals. And so we want to check that our definition of product is kind of a good definition. So I'll be talking about tableaus throughout this talk. So for me, a tableau is a semi-standard Young tableau that has a skew shape. If you don't know of all of this terminology, just keep on with me. I have a bunch of boxes. I have here the outer shape of my tableau is 6, 2, 1, because I have 1, 2, 3, 4, 5, 6 boxes in the first row, 2 in the second, 1 in the third. And I allow to have empty boxes, and I want these to be also partition shaped. I want the rows to be weakly increasing and the columns to be strictly increasing. So that's what I will be using as a definition for tableaus throughout my talk. So once in a while, there'll be straight tableaus. When I'll talk about a straight tableau, it just means it has no empty boxes. And otherwise, I'll be talking about skew tableaus, which is what we have. So sometimes I may use skew if it's for tableaus and just talk about straight once in a while also. Cool thing is that we can associate a tableau to a monomial by looking how many entries 1, 2s, 3s, etc. are in our tableau. So for example, here we'd have the power 1 to x1 because we have only one entry 1 here in our tableau. Exponent 3 to x2 because we have 3 entries 2 in our tableau, etc. So that's how we'll pass from tableaus to the Schur functions that I've been telling you about. And so the Schur functions associated to a partition lambda are going to be defined as the sum over all tableaus of shape lambda with the associated monomials as I've defined in the previous slide. And we're interested in the product of two Schur functions, which can be expressed in this formula. And because the Schur functions, they are a basis of the symmetric functions, well, we can always rewrite this product of monomials in terms of Schur functions because the product of symmetric functions is a symmetric function. And these coefficients are going to be kind of the center of this talk. They're called the Littlewood-Richardson coefficients. They've been studied quite a lot. So you may know that there is actually a combinatorial way of expressing those. And in my opinion, it's not a very natural definition. And so I'm going to try and give you a more natural definition for these, using crystals, jeux de taquin, and product on tableaus. So I will want to obviously introduce all of those things so you can understand my definition. So starting with jeux de taquin and product on tableaus. So jeux de taquin, some of you may know it. It acts on skew tableaus in order to rectify them. So if we have the following skew tableau, it has empty boxes. So we want to remove these boxes by kind of shifting them through the tableau up to out of our shape. And so we can take an inner corner, look at both the cells that are touching it. We want to move one of these entries into the empty cell, and we want to keep the order on the lines and the columns. So here we would have to move the 1 because we cannot move the 2 up because it would not, it would break the order on the lines. So we move the 1, we do the same for the next cells, we move the 2, and this is what I call a slide of jeux de taquin. So it's kind of all the moves of the cells that we have slid through to make the empty cell go outside of our shape. So we can keep going by taking a next empty corner, going again and again until we have a straight shape. And something really important is that whatever order we take it doesn't matter, we'll get the same tableau in the end. So we can pick whichever empty corner we want, we'll always get the same tableau in the end. So now that I've introduced the jeux de taquin slides, I can introduce you to the product on tableaus. So I'll note it by the star product. So if I have 2 tableaus S and T, their product will be taking both tableaus kind of diagonal one from another, only touching in 1 point. The reason why I want this is I would want to be able to kind of read off the entries of both tableaus by reading first the ones in the first tableau, then the second one, and without interfering whether I want to read through the lines or through the columns. So I want the entries to not be interfering one to another. This will have, this is a definition that doesn't come out of nowhere, and you might see why a bit later. So there's this really important theorem from Lascaux and Schutzenberger from 1981 that says this product defines a monoid structure on tableaus, which has equivalence classes under jeux de taquin slides. And so if we take our product of tableaus and we rectify this big skew tableau using jeux de taquin, which we get what I will write as rectification of S star T, these 2 will be equivalent in our monoid. And for those who know about this, this monoid is actually isomorphic to the plactic monoid, which is a monoid on words. The plactic monoid, to talk very, very quickly about it, is a monoid where we concatenate words by the product. You can see that this is kind of what we do with the star product. And we have equivalence relations that are the Knuth relations. And it's actually possible to prove we get these with the jeux de taquin slides. So now we're going to talk about crystals because we want to make sure that our product is well defined. And so a crystal is a labeled directed graph that has vertices as tableaus. We fix a maximal entry because otherwise we'd have an infinite graph, which for now we don't want to have. And we'll be able to go from one tableau into another if they have the same shape. And if we change one entry I in T into an I+1, that's the only change we're allowed to make. And this is what we call the crystal operator on T. And we'll say it's indexed by I if we do change an I into an I+1. So it's a very basic definition. It can be much larger, but that's all we need to know for now. So here is a crystal of tableaux with 2 boxes. So the maximal entry here is fixed to be 4. And so here, for example, we have 1, 1. We changed the last one into a 2. And we could not have changed the other one into a 2 because we would not have had a valid tableau. And so there are specific rules for how we can do this. I'll tell you about it in the end of the talk if I have time. So if you can see, here we have 2 connected components, and each are connected to, are identified by the shape of those tableaux. And these are going to be extremely important. So they are going to be denoted by B lambda. So the connected crystal of all straight tableaux of shape lambda. And for now, we fix a maximal entry with n being fixed like straight up. We don't mess up with this. But what we can realize is that even if we let n become bigger, it will always be a connected crystal with only one source. And the source will be the same for whatever n we pick. And this source will be noted 1 lambda. So it's the only tableau of shape and weight lambda. So for example, if we have lambda equals 5, 3, 2, there's only one way to fill this shape with 5 1s, 3 2s, and 2 3s with respect to the rule on rows and columns. So when we allow n to become much bigger, and if we don't fix a maximal entry, we actually get that B lambda corresponds to the Schur function, S lambda, because we have all the tableaux of shape lambda that will show up in this crystal. So when we have crystal of tableaux, we're allowed to have multiple components. We're allowed to have skew-shaped tableaux. But for each of its connected components, we'll always be able to identify each of the connected components to a certain crystal B lambda. How do we do this? Well, there's this really sadly not so well-known theorem from Van Loven that says that jeu de taquin slides commute with crystal operators. And so if we have here vertically connected components of skew tableaux, well, going down each arrow corresponds to making the same applying the same crystal operators, and going from right to left corresponds to applying a jeu de taquin slide. But all of these connected components are going to be isomorphic. We'll get exactly the same thing. And it actually commutes. So if we apply a jeu de taquin slide, apply an operator, crystal operator, and kind of undo the jeu de taquin slide that we had done, we'll get the same result as if we had simply applied the crystal operators. So this is going to be extremely important in this talk. So now we can introduce the crystal product on tableaux, which is that if we take 2 crystal of tableaux, it's a very formal definition. Each of the vertices will be the formal product S tensor T, for S tableau in the first crystal, T a tableau in the second crystal. And the crystal operators, so how we change an I into an I+1 in one tableau, will be acting on the concatenation of the reading words. So I've left this quite blurry. So just to see, if we have a special vertex as a tensor T, it will be considered to be equivalent to S star T, because the crystal operators, they act on the reading words of the tableaux. And here we only concatenate the words. And we've seen that the star product actually does only corresponds to concatenating the reading words. And we've seen that jeu de taquin slides commutes with crystal operators, so we can actually rectify the shape that we get. And so we could just take the crystal product and do the star product, rectify them, and get the connected components they're isomorphic to. So maybe it's a bit unclear, so let's see an example. So this is the crystal product of the tableaus of only one cell. So we do this formal product, we get these kind of pairs of tableaus, and we can apply the crystal operators. This is what we get. Now we can use the star product, and we get these skew tableaus. And finally, we are allowed to rectify them, and this is what we get. And if you've noticed, we haven't changed. We've gotten an isomorphic crystal at every step of the way. And we noticed that, well, the top right component, well, it was actually isomorphic to B2, and the bottom left component was actually isomorphic to B11. So this tells us that our product is a good product, and it will allow us to understand the Littlewood-Richardson coefficients, which is what we'll see in this last section. So,
Florence, do you are over time?
Okay, let me just finish very quickly. Yeah. So we have that here. This first Schur function corresponds to a crystal of B lambda. The second one corresponds to the crystal B mu. And so we can just consider the product, and we count here the coefficients to be the connected components in B lambda tensor B mu that are isomorphic to B nu. And this corresponds to counting the sources of these connected components, which will be elements S tensor T, such that the rectification of their star product is actually 1 nu, so the source of B nu. So that's all that I wanted to say. Thank you.
Great, let's thank the speaker.
And here are my sources if ever you're interested in learning more.
Great, sorry, I didn't know your ending slide was so much sooner on.
No problem.
I was like, oh, we have a lot of dots.
Yeah.
Yeah, that was great. What questions do we have for Florence?
Can I ask a question? So have you looked at this for like different types of tableau, like set value tableau? Because I know that there is like a crystal structure on set value tableau.
I haven't read anything about the crystal structure on set valued tableaus. Actually, what I've been working on mostly in my master's thesis was ribbon tableaus, especially domino tableaus, and looking at the crystal structure on those tableaus. And there is also kind of a jeu de taquin that agrees with crystal operators on domino tableaus. And that's kind of what I've been working on more. So I haven't looked so much in other tableaus.
Well, the session does end in about 10 seconds, so maybe we can thank Florence again, and then if people want to, if she's comfortable sticking around and people have questions.
Yes, absolutely.
So let's start by thanking her one more time.